I spent a lot of my career in the tech industry building machine learning and data science platforms and solutions. I spent the last 3 years or so at Deloitte, as Adam mentioned, as the basically subject matter expert on machine learning and AI. In the last year or so, we spent a fair amount of time with our clients looking at ethics and fairness in AI, and that's what I would like to talk to you guys today about. All right, so let's get started. A little bit of a warning is this presentation will involve some math. I won't hopefully scare anybody away, but please bear with me. So we're going to talk about fairness today, and the definition of fairness, especially in AI, can be quite tricky. But even outside of it, it's almost uninsightful to say that we recognize fairness through the lack of unfairness. So we know unfairness when we see it. Intuitively, we feel it. In fact, it's so ingrained in us that even monkeys can detect it. In particular, today we're going to talk about fairness with respect to subpopulation with a protected attribute, but we'll get to that in a moment. So what I'd like to start with is a few examples of what is considered unfair. And again, that will lead us into our discussion of how we then apply that to machine learning, data science, and AI. So as I mentioned, even monkeys can recognize when things are unfair. So some of you may have seen the clip that I'm about to show, but capuchin monkeys are taught to exchange rocks with humans in exchange for food. So they give them a rock, and then they have to give it back, and then they get back a little snack. Monkeys like both cucumbers and grapes, but grapes are the better snack. And here's what happens when you create an unfair situation. So as you can see, the monkey gets quite upset when they're happy with the cucumber at first, but then when she realizes that the other monkey is getting grapes instead of cucumbers, she decides that's not fair. So the other issue when we talk about fairness, and part of what makes things are quite difficult is what is fair. So in the picture on the left, everybody's given a single box to stand on. Well, the person who is tall can still benefit from it, but the person who is too short can't benefit fully from it. And the person in the picture on the right, where we consider equity as opposed to equality, we give people boxes according to the height that they actually need in order to be able to see the game. So in machine learning and data science, and you'll see this later, we'll talk about difference between equality of odds and equality of outcome. It creates a different scenario and ultimately changes how we approach our solutions. Okay, so some forms of unfairness and bias that you'll find in machine learning. Now, I'll present these here as if they're intentional. They don't have to be intentional. In fact, often they are not. Gaston gave the example with the credit loan based on salary and gender coming up as an important feature. So the model essentially is testing directly for membership in our protected group, and then gives a different outcome to the members of that group, right? In this case, based on gender. It doesn't, like I said, it doesn't have to be intentional. It can be unintentional, but we still see that kind of bias and unfairness happens. Now, by extension, if we just focus on salary, we remove the gender information, we're not directly testing for the protected group, but it's still, we're still essentially testing for it indirectly using a proxy. You'll see this often in credit cards. By looking at transactions, you can often tell the difference between men and women, and banks have gotten into some hot water. I won't mention any names, but there's been a couple of big stories over the last couple of years of banks giving different credit rates to men and women based on their transactions. So you don't have to have that explicitly in your data set, but through redundant encoding, you might find that the models pick up on that. So marketing decisions can, again, based on years of online data, we don't need to actually test directly for the protected group. Redlining is a specific form of redundant encoding where particular neighborhoods, for example, can be denied services. And if those neighborhoods are highly correlated with particular races, then again, this is a form of redundant encoding for protected group. Again, it doesn't have to be explicitly coded for it, but it'll come out. The algorithms will pick up on those type of signals, and it doesn't even have to be the majority of the neighborhood being of a particular race. We can see that even happening when just the proportion of the particular race in a particular neighborhood is higher than what we'll see normally. That can still create bias and unfairness in the resulting algorithm. Another form of bias that we will see and we have to watch out for is in cases where I'll talk about it as if it's intentional, but it doesn't have to be intentional, where members of the protected group C are selected for favorable decisions, but you don't necessarily pick the right members of group C, and that creates a justification for future discrimination and future exclusion from those favorable decisions. So if you intentionally give loans to a few members of C who, for whatever reason, unrelated to the membership in group C, shouldn't have, then that gives you data points and creates a feedback loop that will then justify future decisions. And that can be held up to justify those decisions as well. And you can do that in the opposite way as well, where you create reverse tokenism. So you purposely pick members of C complement, so people who are not in the protected group, and then you purposely discriminate against them in order to essentially claim that you're not actually discriminating because, look, here's this member from this other group, he's not in protected group C, they didn't make the cut, and therefore there's no discrimination, there's no unfairness. So these are just some things that to watch out for, and we'll see as we walk through how do we measure fairness and how do we address that through algorithms, that these can come up and creep into our assessment and our evaluation, and we have to watch out for those. So unfortunately, life is not fair, but that doesn't mean that our algorithms can't be, and that doesn't mean we shouldn't just raise our hands. It's on us as data scientists to make sure that we create a better world rather than keep perpetuating. One of the biggest complaints that you'll see these days around AI and ML, putting aside some of the doomsday scenario that AI killer robots are coming to us, there are actual issues of putting in algorithms that perpetuate bias and perpetuate and make it sort of okay because as the computer said so, right? And the data justifies it. So Gaston alluded to that a little bit with GDPR, but we have to watch out for that and justify our decisions. And we can actually take this opportunity where we're putting in these algorithms now to fix essentially some of the societal biases and some of the issues that we've created for ourselves. Okay, so how do we measure fairness? I'm going to steer away. I'm going to try to steer away from gender, race, or anything specific. There are a lot of good and bad examples of recidivism models and loans and whatnot. We'll try to keep it a little bit light today, and I'll use university acceptance and admittance procedure as our case study as an using this example. So we got Elite University, located in Fairville, Ontario, and it is very prestigious and hard to get to. They've been criticized for making unfair decisions on their admissions process, and they want to make sure that their process or not, but they want to make sure that they act in fairness going forward. So they invested a lot of time in developing a model with their in-house statisticians that will make their admission decisions, or at least sort of the first steps, filtering for them. Their model, f of x, produces a prediction y hat, where x is the applicant features, so everything we know about the applicant, and y hat denotes the model predicting the students will be successful at their study. We're going to define success in their studies as being able to graduate with a decent GPA in no more than 5 years. How we define success, it doesn't matter, as long as we define it and stick to that definition consistently in our analysis and our work. As well as, I would kind of say that in the case of something like this, we're at a university, we might want to be transparent with our definition of success as well, so that students and potential students know what they're aiming for. All right, I promise some math. Here it's coming. It's a little bit of notation. So y without the hat, it's either 0 or 1, which says 0 means the students will not be successful, 1 is the student is successful. That's our ground truth. And we have some data that we can work with historical patterns. F is our model, as we already discussed. And as you'll see, the model doesn't have to be discrete. It doesn't have to actually output just strictly 0 or 1. It can output distributions across 0 or 1. X is our input, our features about the students. Y hat is the output. A is the output space from the model. And like I said, the model can output actually distribution over that space. And C is our binary class label for protected attribute. So capital C, that would be our set of protected group, and C complement is our non-protected group, general population, if you will. Okay. Along the way, most models don't just output 0, 1. They're going to have some internal risk score. And in general, we'll pick it so that the higher the risk score, I'm using the term risk score because a lot of time we'll do that in loans and banking, but really this is just a score. In this case, because we're going to assume higher scores are favorable, so it's not really a risk score. But the higher S, the more likely that Y equals 1 holds. And we're going to have to set, at some point, we're going to have to set a threshold on S, so that anything above, any person with risk, with a score above S threshold is going to be admitted and predicted as successful by the model. So a label is favorable when some downs should be with an advantage. In this case, that means selecting somebody for admission at the university, and we're going to assign that to 1. Okay, so let's start with how do we measure fairness, and what does that mean? So probably the most naive, but the most straightforward definition is our output, our prediction from the model, is completely independent of membership in the protected group. And now, as we're going to see, this is going to cause some performance issues and actually allow for a lot of unfairness in some senses, just because in general the distributions between the probability of favorable outcomes is different across protected and non-protected group. And for the sake of the notation, for the sake of the discussion, we're going to be assuming that redundant encoding is not an issue. That is, if we're saying that the probability of the output is independent of the protected group, race, gender, whatever it is, we're not sneaking in some other information about it. It really is independent of that feature. So you can assess the statistical demographic parity using disparate impact ratio. This is a particular metric that's been used in industry for many, many years to assess parity between the protected and non-protected groups. So how likely is it to get a favorable outcome given that you are in the protected or non-protected group? So for example, for hiring decisions, we would look at all the applicants from the protected group, all the applicants from the non-protected group, and look at this ratio of who actually got then a job offer. And this is something real. This is covered under Title VII of the United States Civil Rights Act. And in fact, this was put in place in 1978 with the guidance that that ratio cannot be any less than 0.8. That is, people under the protected group should not be getting job offers that are at a rate that's less than 80% in that of the non-protected group. Again, this is looking at, of all the people who applied, how many got a job offer. Turns out that there's a lot of problems with this particular approach. And we'll walk through them through an example. So the university wants to admit students, and they want to admit them according to their ability to be successful, ultimately. But we have a limited number of seats. So from the perspective of members of the non-protected group, C complement, who are likely to succeed, if we enforce this on restriction based on people who are applying, we're going to lose a lot of utility. We're going to have to force a lot of people who are likely to succeed to leave out, and at the same time include a lot of people who may not be as likely to succeed. And we're completely beholden in this situation to our applicants. We don't have any control over who actually gets the outcomes. So we talked about equality of opportunity versus equality of outcomes. Just because somebody applied doesn't mean that there should be X percent of them actually getting accepted. They should still be getting accepted based on merit. But the thing is, you can hide a lot of that under this consistent parities. And here's an example. So if members of Class C happen to be more talented in mathematics and science, but less talented in finance, and it's the opposite for members of the non-protected group, the C complement, if we focus on parity and we select students based on their aptitude for economics, we're going to end up admitting the wrong subset of C. So not only are we not fair in some sense, because we're accepting people who are potentially less likely to succeed, we're actually letting in the wrong subset of people by focusing on parity. And the key here is that this is the kind of problem that will arise when we try to ignore membership in C rather than focusing on it. Now, as we go on through the discussion, you'll notice that you need to know, in order to do any kind of analysis or do any kind of correction, you have to know that membership of C. So in the past, again, the thinking was, if we don't collect that information, if I don't collect gender information, if I don't collect race information, then I can't be biased against it. But in fact, what we've seen is, because of the existence of proxy variables and other things, by not knowing, by not focusing on trying to correct for fairness and bias, you create and perpetuate that bias. Another problem is that, again, you can still adhere to statistical parity, but create situations of self-fulfilling prophecies as well as reverse tokenism. So, for example, if with statistical parity we invite equal numbers of members from the two groups for the interview, but we again pick members from Class C, not correlated to their likely to succeed, and therefore creating the self-fulfilling prophecy bias that we talked about before. You can also, again, with statistical parity, still show members of class complement who are interested ads to come join the university, and again, the wrong subsets of the protected class C the same ads, and therefore the people who will then respond to those ads are going to be biased towards our non-protected group. So again, statistical parity doesn't mean that you're actually picking the right subset or the right people. It just means that you're picking an equal number of people. So based on all that, those issues, the administration decides that demographic parity is not the right metric for them to move forward with, and they're going to look at some other metrics. The next one that has been very popular in industry is what's called predictive parity. So in this case, we want to make sure that our precision or positive predictive value doesn't vary across the groups. Namely, we want that the probability of being correct for the protected group and the non-protected group is the same. When you say that they're going to be successful, this has been widely used, in fact, as a metric up until a few years ago. It was used by the recidivism model in the US to create some big issues because you can achieve this seemingly fair outcome by denying the favorable outcomes to deserving members of Class C. What you'll notice here is that we're not insisting that members who deserve the favorable outcomes actually get it, but rather that the people who got rather that the people that got the favorable outcome deserve it, which is very different. So now we're going to get into some of the stricter measures, the stricter criteria, and the first one of which is called equal odds. So in this case, we want exact fairness between the protected group and non-protected group, and we're going to demand that the outcome, so given the outcome, the probability is the same whether or not you're in the protected group or not. Okay, so this now alludes to what I was referring to before. So people who deserve the favorable outcome get it with equal probability whether or not they're part of the protected group, and people who don't deserve the favorable outcome get it as well with the same probability. Okay. Another way to say that is that we want both the true positive rate and the false positive rate, also known as recall or fallout, to be the same. And by extension, you also hear this referred to as balanced error rates, because false positive rate is obviously a false positive rate. True positive rate is one minus our false negative rate. So therefore, our error, the rate at which we're making errors, is the same. Again, this is given whether or not they deserve that favorable outcome, the ground truth. And this can be achieved by operating at the intersection, essentially, of the two RC curves. So if you look at the different RC curves that will likely result for the protected group and non-protected group, and again, I'm assuming here some background knowledge about the statistics and the RC curves from this audience, but what it amounts to is then finding that point on those two RC curves that intersect. At that point, we'll have equal error rates for both and equal odds. Unfortunately, that's not always the case. You can't always, the RC curves sometimes don't intersect. One can be just, for example, on the inside of the other. And there is a way for you to do that then, which involves some randomization. So if you can't operate at a point where they intersect, what you can do is you need to pick 2 points on each curve. Below SC mean, you reject, there's a mistake here on the slide, please bear with me. When it's below SC mean, the members of group C are rejected. When it's above SC max, the members of group C are accepted, are admitted. And then when the scores are between the two thresholds, it's random in such a way that essentially what you're doing is you're creating a scenario where the ROC curves do intersect in that region. One of the problems with this is that you lose a lot of utility. You're going to ultimately end up with a much worse model than you can by using some other, hopefully valid definitions of fairness. And in particular, this kind of classifier that requires equal odds, it basically has to adhere to sort of the hardest group to classify. The hardest group to make decisions for will dictate how everybody else gets their decisions made as well. Okay, equal opportunity, on the other hand, is a slightly less strict criteria, where instead of demanding that both people who deserve and don't deserve the favorable outcome get it at equal rates, we only demand that the people who deserve the favorable outcome get it at the same rate, regardless of whether or not they're in the protected group. And in general, this is the definition that has been the most widely accepted going forward. When it comes to fairness, it's the one that we recommend, and it's the one that we kind of push for. Essentially, what this allows elite university to do is they can take now advantage of the higher predictive power for the non-protected group, but still protect themselves and protect their applying students from unfavorable scenarios when they don't deserve it. Now, one thing to note is that while group outcomes might be fair, individuals can still be discriminated against. And in particular, two very similar individuals may get drastically different outcomes while still maintaining the group fairness of equal opportunity or equal quality of odds. One way to address that is by requiring that, of course, that similar people are treated in a similar way. And this has been formalized by a group at University of Toronto by saying in the following manner. So we have some metric that takes in two students and creates a score of how similar they are. And similarly, we have a metric that takes out the output from the model, or in this case represented by a distribution over outcomes, 0 and 1, rather than an exact outcome. And again, takes that distributions and evaluates the distance between those 2 points as well. And a fairly straightforward definition then is the Lipschitz Condition, which says under those two metrics, the model is fair if the distance metric between the outcomes is less than or equal to the distance between the inputs. So let's create a smooth mapping essentially from the input to the output. That's why we have to represent the output as a distribution over outcomes rather than a single outcome, because no matter what we do with, we're going to have to have a steep step from 0 to 1, which obviously will violate this condition. The bonus is this eliminates problems of reverse tokenism or self-fulfilling prophecies because you're enforcing the similarity metric. However, notice that on its own, this is not sufficient to guarantee against anything like quality of odds or quality of opportunity, because you're not actually making sure that, because if the two groups have very different properties, you can still meet the Lipschitz condition, but violate group fairness. So you actually need to impose this along with the group fairness requirements. And of course, the challenge with this is now elite universities trying to figure out just exactly how to fairly measure that similarity between individuals, which might not be so straightforward. Okay, so I throw a lot at you, but the last thing I want to leave you with is the two key fairness metrics that we talked about. One required that people who deserve the favorable outcome get the favorable outcomes. The other one was that the people who get the favorable outcomes do so with equal rates. Essentially, if you go with quality of opportunity, you will create a scenario where you have to do some affirmative action, for lack of a better word, where you're going to have to allow people who don't deserve the favorable outcome to get favorable outcome from the protected group in order to make sure that you don't leave people behind. But that, of course, creates a disparity in your precision, in your predictive parity. So, and essentially makes it easier, if you will, to get accepted if you are part of the protected group. So what if we want to try to go for both? We want to make sure that people who deserve the outcomes get it, and the people who get the favorable outcome deserve it at the same rates. So we want to best of both worlds. Well, here's a very fairly straightforward proof of why that cannot be. So predictive parity, precision. So we want to have that the same. And similarly, we want equality of odds, so balanced error. So our false positive rate and our false negative rate all to be the same across both groups. Let's do both. And I'll leave you this a quick exercise. If you just plug in the formulas, it's pretty straightforward to show that the prevalence, P over 1 minus P, times the predictive odds, 1 minus precision over precision, all times the true positive rate, equals to the false positive rate. And of course, by extension, this is true for each group. And now if we plug in the same, so we want to have the same precision, the same false negative rate, the same false positive rate, that implies that the only way that that can happen is if the prevalence, if the initial probability, P0 and P1, are the same. So that means that we can only achieve this in the fairly trivial case where the overall likelihood to succeed is the same in our protected group and non-protected group. This is generally not going to be the case. Otherwise, we wouldn't be in the mess we're in the first place. So how can you do this in practice, and how can you actually achieve this? One of the most common and straightforward ways is you actually change the input. So, for example, you can change the label on some of the inputs that are sort of near the threshold and push them over the edge. So you actually change slightly the definition of what needs to be successful in this case, and make sure you have enough representation so that the overall prevalence, like what we just seen, is equal. That will generally lead to a more fair algorithm. You can change the loss function. So if you're doing something with logistic regression, neural networks, it's very easy to change it. With some of the algorithms like XGBoost or random forest, you might struggle a bit more, but you can actually change the loss function and, for example, even add the Lipschitz condition into it by creating a penalty if you disobey it. The other one, you can also add a loss function based on the equality of odds or equality of opportunity, so that the algorithm is forced to obey those a bit more. And then lastly, we mentioned already using different thresholds, but you can actually also just trade out different models in order to kind of try to get the best of both worlds, where you do the best model you can for the protected group, the best model you can for the non-protected group, and then make sure you operate them at the point of fairness. I'm going to wrap it up here. So obviously, one thing to take from this is fairness is not easy. Even just defining fairness is still a contentious point. I've mentioned to you the definition that we've aligned on and some big parts of the industry have, but that doesn't mean that that's the end of that discussion. I'm sure that will continue on for many years yet, trying to come up with other ways to define fairness. Bias can creep into the data set in subtle ways. I mentioned a few in the beginning. It doesn't have to be intentional, but it can still happen. So you have to actually focus and be aware of those issues in order to try to fix them at the source, at the data. Knowing how to measure and fairness and bias, it just has to become part of the way we do data science. Otherwise, we can't just rely on the data. And that alludes to another point which we love to make. As a data scientist, you should never be working on your own with the data. Always work with in this case, the administrators, but always work with the business owners, the people who understand how the data model is going to be used and what effect and implications it has once it's put into practice. I didn't go into it today, but there are toolkits that are available to help in the process. Some of them are open source, some of them pretty much all the big names are offering on their cloud platforms various tools that allow you to peer into the algorithms and do obviously feature importance like Gaston has mentioned, but also look at it from a fairness perspective and bias. But again, in order to do that, you have to have access to the protected variable in your data.
What regulatory body in Canada is the equivalent to the GDPR in the EU? Yeah, that's a good, interesting question.
So GDPR is, I believe it's a regulation, not a regulatory body. I can't remember the name of it now, but the R is regulation. Um, in Canada, we have OSFI. It's specifically for financial institutions.
How did you spell that one, Ofer?
OSFI.
Mhm.
It's the Office
Of
of
Superintendent of Financial Institutions?
Financial Institutions. That's the one. Um, and they provide all the regulatory information, all the regulations around financial institutions and what they can, can't do in terms of algorithms and data and explainability. There isn't, the other one is the Office of the Privacy Officer. They deal with data privacy. So they provide a regulation around what companies can and can't do when they collect data and how to share it. But there isn't an equivalent sort of, at least not yet, of the requirements from GDPR, which is any company doing anything with any data has to be able to explain that information to somebody who was affected by that decision, by decisions made on that data. So we don't have that equivalent yet. But for better or worse, most of the tech companies, do business around the world. Since they have to adhere to GDPR in Europe, they've all changed their processes so that they're GDPR compliant, regardless of, not just for people in Europe, but globally.